Good day. This is Mike, and I'm going to talk to you about the important idea of a planar curve. Let's begin by a question. How do you describe the path of an object? Perhaps this object is moving very erratically. I'll digress for a moment. So you've probably heard this statement that two wrongs do not make a right, and this is very true. In fact, it's good words to live by. However, as it turns out, a very wrong can make you famous. So to explain, in 1988, there's an English botanist by the name of Robert Brown who observed a very erratic motion of a pollen grain immersed in water. This grain was continually being bombarded by waves, by little microwaves. And the path looked something like this. So it started at some point, and it was always turning, always abruptly changing. I cannot possibly draw it rough enough. And of course, as time went on, it was moving in a particular direction. Maybe I can highlight this with a little different color. And so it is moving with some direction, and it's going through this very, very erratic path. And this was an important discovery, and it's now called Brownian motion. In this case, it would be a planar Brownian motion, but scalar Brownian motion is used to drive stock price models, and it truly is one of the most famous and celebrated probabilistic models around. So Brown speculated when he saw this, and this is where the wrong comes in, the extreme wrong, that he was observing a primitive molecule of life. He thought, well, this doesn't satisfy any of the smooth physics, and so this must be some type of life form. Of course, he was wrong, which he later proved. But if we look at this, and we could ask this question, well, why does our basic knowledge of functions, why does that not work for this path? And really, there are two reasons. So first of all, if we were to draw some type of line, or a horizontal or vertical line, what we would see is that this path crosses these lines multiple times. So we could say, why can't it be described as a function? Well, it doesn't pass the vertical line test. So that would be one reason. But there's another reason, and that is one of the important ideas here in this path is the notion of what it's doing as time passes. And so a function can't capture, so maybe say a function can't capture the time evolution. Okay, so let me just explain for a minute, just be careful. What we really mean is just that XY function couldn't capture the time evolution. What we need to do is bring time in somehow, and that's the idea. But it's important to know that we can still graph things. So just as we drew this Brownian motion, we can draw things that aren't functions, so that do not pass the vertical or horizontal line test, i.e. they're not generated by function curves. So they're generated by something more complicated, or simple XY function curves, maybe to be more precise. So let's just go through and look at what we know. And we already know some things already from high school and from our first course in calculus. So first of all, there are, of course, a lot of curves that do correspond to functions. Okay, so we know about continuous functions, but we could have a discontinuous function. So we could have a function here that has a jump discontinuity. And it also could have an oscillatory discontinuity here too. So there's two discontinuities here. but it's still a function. You know, if we draw a vertical line, the function only crosses it once, so it still is a function, just a discontinuous one. You can also, in functions, of course, can have gaps in a domain. So this is a function where it's not really defined, or it's not defined on sort of this half closed interval here. So it's not defined on that spot, and it's also not defined on this interval here. So this doesn't matter. It's still a function. You can still draw vertical lines and see that it only passes. In fact, this function is continuous. It just has gaps in the domain. We can also have a different type of function, and so we can have functions that look like they've been flipped in the y is equal to x line, which they have, and so we can have functions of an independent variable x. Okay, so instead of passing the vertical line test, to have such a function, we need it to pass the horizontal line test. So what we can see, that if we draw a horizontal line, any horizontal line at any level, so any place in the domain, which the domain now is in the y-axis, it only crosses this curve once. So it is in fact a function, just a function of independent variable x. But there are also curves that do not correspond to functions that we're familiar with. For example, like a circle, or more generally, an ellipse. So we have an ellipse drawn here with a center at x0 and y0, and then it has a major axis and a minor axis. But what we can see is, if we drew any vertical line, well, it doesn't pass the vertical line test. And if we drew any horizontal line, well, it doesn't pass that either. So this is not a function. It's possible to split this up so it is two functions of either x or y, but it's certainly not just one function. We also will recall the hyperbola. So in this case, it's a horizontally transverse hyperbola, and so it opens to the left and to the right. Again, this has the center point here, which is x0 and y0. So this is not so important for us, but the important thing is that we remember what a hyperbola is. And again, if we were to draw a vertical line, it's not going to pass it because it crosses, a vertical line crosses this curve twice. And same thing with any horizontal line. Again, it will cross this curve twice. So this cannot be a function. And once again, in this case, it is possible to describe it as two functions, but not one. Another interesting curve is that of an asteroid. And so this kind of looks like a saggy diamond. So it comes in every case, and it comes out to R in each case. And we'll study this, and we'll describe this as this term goes on. But once again, if we're to draw any line, it's not going to pass the vertical line test nor the horizontal line test. So it's not a function. Again, one could see it could be two functions, one for the upper part and one for the lower part. So it is possible to describe these ones as two functions. Okay, so just for clarity, these last curves do not pass either the vertical or horizontal line test. And so they're not functions. But we can still draw them. And so what we should do is we should think, well, if we're going to describe them, we should also think about, well, how would we draw them? So let's just look at this, and we could ask ourselves, well, where would we start and where would we finish? And maybe we could indicate the direction of motion. So this is an important and useful exercise. So we could come back to here and we could say fairly arbitrarily, well, what we're going to do is we're going to start here, and then we're going to describe this curve. We're not going to worry about the mathematics to describe it at this point, but we'll get into that. We could say, well, if we're going to draw it, we're going to go around here. We're going to come up to here, and then we're going to go here, and then we're going to go here, and we're going to go along here, and then we're going to go, finally, we're going to go along here. And we're going to come back, right back to where we started. So we can do that, and we can go back to some of these other ones, and we could indicate maybe in this ellipse, maybe we start here, and we go around the ellipse in this direction. And in both of these cases, this is going to be the most natural thing to do, as we'll see as we move on. The hyperbola, maybe what we do is we would start way out in infinity, and we would come along here to transverse the right-hand side of the hyperbola. And we can go back, and even the functions, there's no issue. We can also transverse them. Maybe we start out at minus infinity, and we transverse this in this direction. That is no problem. And we can transverse this, say, as is most common, going from left to right. So we could go in this direction. And even this oscillatory one, well, it's a little bit more difficult because it is oscillatory portion here, discontinuity here. So we might have to do this in two pieces. Maybe we transverse this piece, and then maybe we start over here and we transverse this. But in every case, whether it's a function, multiple functions, or in the case like at the beginning of this Brownian motion, not any function at all, we can draw it, we can describe it that way. And that's the start of the idea of curves. And so in closing, I'd ask you these questions. How do we describe such curves? Well, we've all come across equations like x squared plus y squared is equal to 1 for the unit circle. That would be an example of an implicitly defined curve. Or parametric equation. Well, that's where we're heading when we're drawing this. And so for the circle, again, we could say x of t is equal to cos t, y of t is equal to sine t, and that would transverse this circle, and we'll explain that in a following lecture. And how could we describe something that's not even a function at all, like a Brownian motion? Well, in that case, we are limited to these parametric equations. Thank you.